Hello. Uh, as best as I could, I tried to fix camera. So I'm wondering how high quality it might have. Forgive me in advance kindly. Um, uh, Two experiments we carried out last time. Weak acid titration and buffer preparation or buffer generally. So I'm trying to separately explain those ones. First one, weak acid titration, just how to write lab report. By the way, from tutorial you have to take notes because you need that for your final exam, and it could be you have to take it into account, otherwise you fall in trouble for final. Weak acid titration. For introduction, so after those headlinings, you may start by introduction. As ever, you may find out stuff over the internet and find out some general information like background, history, and finally hypothesis. So generally, you expect when you titrate a weak acid by a strong base, firstly, particularly you want to find out what is corresponding pH inside container, So firstly, it is weak acid, and then after a while, dropwisely you leave drop by drop base and drip it to the container, beaker, in our case. After a while, it tends to buffer, and then purely basic it's going to be. So it is your expectation, your hypothesis. Just I very oversimplified that for you. You may write it in a coherent text. Then for the next part, materials. We had beaker, sodium hydroxide, acetic acid, titration stuffs. Titration setup, a stand, gloves, and burette, whatever. Stirrer. Now we've got multifunctional hot plates, so simultaneously you're able to both stir your chemicals and heat it up. And magnet. What else? For a moment, for weak acid titration, that's enough. Besides some equations you needed, we said at least molar, mole over liter, need to know it. And Henderson-Hasselbalch equation, pKa plus logarithm of A minus over HA. And finally, pH, 14, let's start from pH, minus logarithm of hydronium concentration, and POH minus logarithm of hydroxyl concentration, and 14 equals pH plus POH. That's it. This is your material part. So all those equations, since we claimed equations are kind of tools in your hand, that's why proper place for equation is in material part. Then بچه یکی دو دقیقه دیگه همین کرار رو از این لب دومی نبود فقط اونجا دیدم فارمت زنده باشه. Then method. For method part, we want you to write it in paragraph format, so just schematically I'm explaining what we did, then you may write in your own style. We said we've got titration setup, and here a beaker filled by, I was wondering how many milliliter, it was probably 50 milliliter, if I'm not making a mistake. 50 milliliter, 0.2 molar, and then sodium hydroxide, 300 milliliter. So we said, if you remember, or if you took a note, you remember firstly, we said NaOH addition, pH. We said firstly, we found out theoretically what is the pH in a beaker. Just it is a weak acid titrate, a weak acid partially dissociated is going to be, and then we continued. But in terms of method, for a moment you're not dealing with calculations. So 50 milliliter we had it here. We found out pH. Then 100 milliliter we added. Then once again we found out pH. Whilst all of it is above the stirrer over the pan, and then there is a magnet here, so it gives homogeneity, it makes it uniform whilst stirring. And after 200 and 300 milliliter, and we recorded corresponding values, particularly for equivalent point. So you have to write it. Once again, I'm telling you, I do not want you to write it schematically, although schemes are good, but main part is paragraph format. And then raw values. All raw values, not perfectly I remember, but as far as I remember, 50 milliliter CH3COOH, 0.2 molar, and 300 milliliter NaOH, 0.05 molar. What else? Only for raw values. If any other values you remember, just record it here. In data processing, let me clean up everything, then for data processing more space we need. Fortunately, when I'm recording video, you do not need, I do not need to stop for you to write it up, since you are able to stop it, pause it, and then whatever you need, how long you need to keep it, very long lasting screen, you may have to take a note. Data processing. Let me check camera. Yes, perfectly. It is recorded. For data processing, so all calculations must be written here. You have to leave them here. For we started from a weak acid, CH3COOH. It was dissociated partially to hydronium and acetate. Then we said initial concentration for acetic acid was 0.2. I'm too forgetful, I hope that I'm right. 0.2 molar, so it's going to be dissociated partially, parts come in corresponding polysus, proper polysus. And then K acidic equals products over reactant, and K acidic equals, X squared. Since we are going to find out pH according to the table, we said we have NaOH addition and pH. So according to table 0, 100, 200, and 300. So right now we will find out what is pH when we have inside beaker just purely acetic acid. That's why I start by weak acid dissociation to find out hydronium concentration by getting minus logarithm. It leads me to pH. So let's say x squared equals, so we seek for x value. Ka times parentheses minus x squared, Ka 0.2 minus Ka x. So we ignored that value. We said x equals Ka times 0.2. That one represents hydronium. So we said pH minus logarithm of hydronium concentration, or minus logarithm of this x value. Just x value must be substituted, plug into the P function and gives us the pH value. So initially it's over, and then we start dripping strong acid to the, but with very diluted strong acid, I mean, to the beaker. So for the first one, we may found it out. As far as I remember, it was like 2.7, more or less. You have to calculate it, since I estimated probably 2.7. Even in class, you saw that I was not tending to calculate it. It took from the life. That's why I was not tending to continue calculations there. And then we said, after 100 milliliter addition, what was going on inside beaker? So we said we start, since we have titration steps, and here beaker. So we start calculating NaOH drip into the acid. So after 100 milliliter addition, we will find out what will be corresponding pH. That's why you've got to find out number of moles for base and number of moles for base and number of moles for acid. Then they may cancel out each other to find out what will be remaining number of moles and sub to molarity. So let's start by number of moles for base. OH, it is a strong base, no matter whether I'm writing NaOH or OH, it's going to be dissociated completely. So let's say it is 0.05 molar. Molar, we said moles over liter, and we spend 100 milliliter. So number of moles equals 0.005. And for acetic acid, we said 0.2 molar means mole over liter. We had 50 milliliter. That's why number of moles will be 0.010. And now we have number of moles for both acid and base that are going to react to each other to neutralize each other. Neutralization reaction must be written then. Next. CH3COOH plus hydroxide gives us water and acetate. So let's say for acid it is 0.01. For base it is 0.005. That's why it's going to finish first as kind of limiting over, and the other ones, some parts of it unreacted will be left over and unneutralized. So as much as we lost here, we are going to gain on the other place, on the other side, 0.005, and that's it. Then we said, right now we wrote neutralization reaction, just acetic acid and acetates left over. We have to find out corresponding concentration. That's why it's number of moles. Moles over volume gives us concentration. So totally 50 milliliter we had inside the beaker, and 100 milliliter we added, totally 150 milliliter. So we said both of them gives the same value, 0.033 molar. This is concentration for acetate, and remaining acetic acid unneutralized. And then we said, since these two concentrations look the same, that's why it leads us, it reminds the Anderson-Hasselbalch equation, corresponding buffer solution, pH equals pKa plus logarithm of A minus over HA. So we found out concentration for these two ones, 0.033 and 0.033. So fraction equals 1, logarithm of 1 equals 0. So we got rid of this part, pH equals pKa. Ka for acetic acid, you may find it out from the internet by surfing over the internet for acetic acid. And pKa probably 4.74 it will be, so pH equals pKa, and it must be recorded here. 4.74. Next, let me recheck the steel. It is resisting. They call it resilience. So my camera is normally not recording for a long time. Hopefully right now it comes as well. My old companion. Right now, we'll see 100 more milliliter we are going to add it, so totally 200 till now. We'll see what will be going on inside the beaker. So let's say once again, we start from hydroxide. It is 0.05 molar. Molar means mole over liter. So the 100 more, it means totally 200 milliliter. Right now, corresponding number of moles will be 0.01. For acetic acid, it is 0.2 molar, moles over liter. The number of moles that was 0.01. Persistently, we have the same value for number of moles for acetic acid, according to our assumption. So neutralization reaction plus OH gives us water and acetate. Number of moles for each must be plugged into the propolyze, 0.01 and 0.01. So it comes here, and the other one right below the hydroxide. So they're going to neutralize each other completely. That's why neither acid nor base will be left over. And the only things left over is acetate. Right now we are able to find out concentration just for conjugated base, acetate. Number of moles over total volume, 200 milliliter we added, 50 milliliter we had, that's why 250 milliliter must be recorded here. We said 0.4. 0.4, or probably some decimals I'm making mistake. Later I'll fix it up, correct it. All my calculations need revision just to get the idea I'm explaining. To go over what we did inside the class for tutorial and laboratory. And then for the last part, oh, by the way, so we said it gives us acetate and water, and it is kind of equilibrium. It's going to yields back the, it flips then, and gives acetic acid and hydroxide. So we are going to continue COO minus, and water gives us, it gains hydrogen, gives acetic acid and hydroxide. So we found out concentration for acetate. Partially is going to be disassociated, part comes here and here. So K basic equals product over reactant. That's why X equals root square KV 0.4 if we ignore the other value. Soon after you found out X value, X represents, if you look at here, X represents hydroxide, not hydronium. So Px means P hydroxide. We are going to have P hydroxide. Just you substitute this value here. Means minus logarithm of Kb 0.4.